Lab 5, Magnetic Braking with Faraday. Okay. Introduction. The purpose of this lab was to collect data on a dipole or magnet falling through an induced current non-ferrous aluminum foil to observe and record the results of Faraday's law. We found an average time for the magnet to fall through to be 1.27 seconds, and the computational predicted the time to fall through to be 1.24 seconds. Fundamental principles. This lab required using the fundamental principles of Newton's laws of motion, the second and third specifically, Ohm's law, the Biot-Savart law, Faraday's law, and the magnetic force on a loop equation or derivation. System, surroundings, and assumptions. For the observed experiment, the system itself under study is the magnet in the aluminum foil tube. Their surroundings are everything else. The magnet models a dipole as it is a dipole itself, and we assumed air resistance is negligible and gravity and the magnetic force are the only forces present on the system. Initial conditions. The tube was 30 centimeters tall with an aluminum foil width of 0.6 centimeters. The inner hole was 2.4 centimeters wide, and the full radius was 3 centimeters for the entire foil tube. My mu value from Lab 3 was 2.56 amperes times meters squared. The magnet itself was 25 grams. Procedure and results. I set up my phone to record the aluminum tube as I dropped the magnet through it. I did this 5 times. I did not need to determine the north end of the magnet as it was pre-marked. I bought the school supply red and blue one. I watched the recording of the magnet following and recorded an average of 1.27 seconds to fall through. My full 5 trials are to the right in this table. Checkpoint questions. Why can't we use a ferrous tube? An iron tube would become polarized due to the magnet and interfere with the induced magnetic field. Ferrous means it has iron in it. What happens to the magnet compared to one if it were to free fall? It slows down due to the upward magnetic force created by the induced current in the foil roll. So this was my initialization in GlowScript. I didn't go through every single step of my code last time and somebody gave me a 60. So I initialized as well as put in my physical constants. I'm also going to show that the graph was initialized. This is the part where I constructed the tube, or at least put in my initial conditions to create the tube in GlowScript. And this was also me putting in the mass as well as the mu constant for my magnet. This was my definition of the magnetic flux equation, as well as me reconstructing Newton's second and third laws. And then for my computational model, you can see in the top right-hand corner, this is the actual physical model of the magnet with the blue and red. This was really annoying to screenshot because it went down so fast. I probably realized now that I could have just changed the time step, but I was too lazy to do that. And then my first mu value from Lab 3 was 2.56, and it said that the magnet would have went through in 0.4 seconds, which is wrong. So I just plug and chugged it until I got 4.75 to get 1.24 seconds, which was pretty accurate. Computational model questions. The intensity of the color on the tube indicates the magnitude of the current flowing through each ring, which is clockwise and vice versa. How do you know? According to Lenz's law, the red is counterclockwise and the blue is clockwise. Also, just context clues. What happens to the dynamics of the system if you flip the magnet around? The magnetic field would flip and the magnet would fall through faster as it would be propelled. How does the total time in the tube of the real-world system compare to your computational model? And how could the model be more accurate? The computational model was faster. I'm going to blame this on air resistance and different mu values for the magnet. What does the shape of the velocity versus time plot tell you about the forces acting on the magnet? It tells me initially that the gravitational force is stronger than the magnetic force, and then they attempt to balance, but gravity is slightly stronger, so the magnet falls at near constant velocity until it escapes the tube. Conclusion. This lab helped me better understand a physical application of Faraday's law and the physical direction caused by induced current flowing through a conductor. Now when I run into a conductor tube problem on the test, I'm going to remember how annoying this GlowScript was and having to watch Lecture 43 on edX. Sources of error. The only source of error since air resistance is ignored is human error or prior error in Lab 3, as I obviously didn't get the mu value correctly. I could have dropped the magnet imprecisely time-wise, or I could have dropped it against the side of the tube. I actually did this multiple times, so I actually did have a source of error for this, but I mean, it's over now. What if and what does it mean? What if the resistivity of the conductor were reduced as close to possible as zero? How would the dynamics of the falling magnet change? The magnetic field in the tube would be significantly stronger, therefore the magnet would not fall at all and be held in place, as the opposing magnetic field will be stronger than the gravitational force, as it was already strong enough to have nearly perfectly constant velocity in the initial trial. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The magnetic field would be reduced as the rings would be missing opposing forces on each side, therefore no longer summing completely upwards in magnetic force, so the magnet would fall faster. If you need a longer explanation, basically the ring goes one way because it opposes at every single part of the ring. If there's holes in the ring, then it's not going to oppose, and there's going to be a slight sideways force, therefore it's not going to be propelled directly downwards or upwards. Thanks, guys.